on Friday. Ben and our lectures will go tomorrow and Friday. So take it away. Thanasis.
Okay. Um, uh, so I have written a summary of what we have done so far, so we don't waste too much time, because I certainly would like to use tomorrow's lecture to talk about water waves, because this is what most people are interested in, and I will certainly do that. And if I don't cover what I want to, I will just skip the part on elliptic PDEs and go directly to water waves. But let's finish this. So what is the idea? The idea is we're giving a PDE. For convenience, we took a PDE of the most elementary possible type. But in the presentation, I have presented material in such a way that it's clear in every step that you can do it for any PDE, and it will become clear even. I'll give you a second example in a moment. So the idea is that you write this equation in divergence form, and I mentioned that you have an explicit formula for evolution PDEs, but also there's a generic way to do it by using the adjoint, yes? And in this way, you get, by integrating around your domain, what I have called global relation, which is this relation here. And I have called global relation because clearly it contains global information, yes, because there are integrals around the boundary. And by the way, it is already clear, just as a prelude to what we'll do, that this is nothing but a very elegant characterization of a Dirichlet Neumann map, you see, because it only involves boundary values. Of course, for evolution equations, you remember I cheated a little bit and I put here t, but if I put capital T, it's clear that it only contains boundary values. And there's nothing more, there's no more information. Doesn't matter how clever you are or how stupid you are, all the information, implicit or explicit, the Dirichlet Neumann map is in this equation. And to me, it's shocking that such an elegant equation was not appreciated before, you know? Okay, and then what you do, you invert this equation, and after you invert this equation, you find the top line, but the integral is along the real line. And then for reasons which I try to motivate, there's two steps which I cannot motivate very well. One is, why should you do it in divergence form? And the only motivation I have for this is a connection with integrable systems. And the next step is, why should you leave the real axis and go to a complex plane? And the only motivation I have for this is this lack of uniform convergence, you see? And then we come to this equation. However, our main problem still remains, because the main problem is that, you see, if you're doing the Dirichlet problem, and this G1 tilde, by the way, note that this is some kind of generalized, here, very good. This is some kind of generalized Fourier transform, yes? If actually there, this T was not there, and in a moment I'm going to take it away, you see, this will be precisely a generalized Fourier transform, because the only exit dependence is in the Fourier transform form, you see? And these are some kind of generalized Fourier data. Indeed, this is the Fourier transform, and this is some kind of T transform. So there's nothing, it's absolutely natural. This is what you would expect, you see? And so the question now is, can we eliminate the unknown boundary values? Or to be more precise, can we eliminate the transforms of the boundary values? Because that's all that enters in our equation. And this is a great advantage, actually. And the answer is, as I already alluded to, yes, we can, by making use of this equation. Because already we use this equation, but only on the real line. While this equation has a much larger validity, this equation is in the whole lower half plane. Okay? So let's look at this equation. You see, let's suppose we're doing the Dirichlet problem. And you see any problem is the same. Let's suppose with the Dirichlet problem, then we know this equation, and we know this equation. Yes? So naively speaking, you say, okay, let's suppose that by some miracle, which will happen, this term doesn't contribute for a moment. Because after all, if this term is there, you know, if we knew this term, there's nothing to do, yes? So let's suppose for some miracle this will drop out. Then in principle, I could say, okay, I can solve this equation for G1, I put it here, and I'm done. Algebra. Not quite so, because look, this, we need it on the contour, which is in the upper half plane. While this equation is in the lower half plane, yes? So this equation is valued in the wrong place, Furthermore, it also involves this, we don't know. But then you use another very important idea in mathematics, which is invariance. Yes? You look at this equation, and you realize that your unknown functions don't depend on k, but depend on k squared, which means your unknown functions will remain invariant by any transformation which leaves k squared invariant. In this case, the problem is trivial, so the only transformation is k to minus k. So if I use this transformation, the global relation becomes this. I don't write inside. This will be plus, but now will become minus. Yes. And this now is valid for k in the upper half plane, which where I want it.
Sort of a naive question.
Yeah. Any questions?
You have this which is valid in the lower half plane.
Yeah.
Why don't you do an analytic continuation of the upper?
Well, you can think of this as an analytic continuation. Yeah, you can think of this as an analytic continuation if you want, but you know, my analytic continuation must be such that I will preserve, I need this function. So whatever I should do, I shouldn't change this. And you can think of this as an analytic continuation, you see? So now I can solve this equation, let's say, for this. Yes? So I will get G1 equals algebra U0 minus k minus ik G naught minus e to the minus k squared t u hat of minus kt. Okay? So let's look at the last term. Yeah? The last term will look like what? The last term will look like the integral along here, e to the I kx minus k squared t. But now look, g1 is this, so it will give us minus 2ik g naught. Okay? Then it will give us plus u naught of minus k. And then look, this very nice thing. Why this doesn't go? It should go. What is plus? There must be some plus here, I guess. There must be some plus here. It's the only way. So this will be a plus. Because it has to go. So now it goes, and this becomes this, the extra term, yeah? And now is the miracle I was talking about. Huh? Please look at this term. Please look at this term. You see, here I have this, you see, this term, of course, it's bounded analytic everywhere in the upper half plane, you see, but this is bounded here, you see.
Thanasis?
Yeah.
Just you, not.
Thank you.
Yeah.
This is bounded analytic here, you see, which means that this, of course, gives a non-trivial contribution. But look at the miracle here. You see, this term only involves this. Of course, this is bound analytic in the upper half plane. Yeah? This, remember, the Fourier transform is in the lower, but it took k to minus k, so it's analytic in the upper half plane. So this whole thing, by integration by pi, and this goes away. And that's the miracle. So the end of the story, you see? So now you have a representation where instead of the last of this term, you have something which you absolutely know. Yeah? If you were doing the Dirichlet problem, the normal problem, it would be no different.
I just have
Yeah.
one question before you put that
Yeah.
down. In your definition of g tilde j on line 2, you have that exponential. Is it e to the minus k squared s?
See again?
The
No.
formula for G tilde?
You're observant, but not 100% observant. Because look, here I have k squared, you see? Here I have k and k. The reason I do this is because in every problem, that's the only integral you have to compute. You see? The dispersion relation will change, but then what will happen will be omega k there. You're right, of course. Yes? No. All right. So for the Dirichlet problem, this term then will be and it's as explicit as you want, yes? But it has more advantages than being explicit. So I will not spend time, although it will take only 5 minutes, which I don't have, but let me just make 2 remarks about this representation. So is this clear? This is the main idea of the method, nothing else, you see. This is the key step. Everything else, as you will see, in all problems, the same idea, okay? And already you understand what happens, because you see, when you go to higher order, you have more unknowns, but more invariants, so more algebraic equations.
Excuse me.
Oh, please.
In order to understand better.
Yeah, yes.
In theory of Hermander's theory of elliptic equation, if you solve the equation in half space, you can replace it by the problem with the whole space using right hand side, like Dirac measure on this line. It is the same?
No.
Where
No.
is the difference?
No.
I mean only for fixed P.
No, there's no
My
difference, you see,
calculation.
because this replacement of, I know this, you see, there is, you see, what this would amount to is if I was trying to extend this to the full space, because this is where I have information, but I don't do this at all. Actually, I do exactly the opposite. I can talk this more, but let me not. But the answer is no. The answer is no connection at all. Actually, it's exactly the opposite mentality. So I get rid of this because now you understood it, but I make some remarks. The first remark.
No connection, your answer.
Huh?
No connection between Hermander.
No, absolutely not. Absolutely not. So let me, actually the opposite. Let me make 3 remarks. The first remark is, you see, remember, up to here everything is fantasy. So at some point we should make this rigorous. This equation now is well defined, so I can start from this and do all the stuff we know, yes? So in order to do this, it would be, for example, convenient not to have t in here, right? And the answer is you shouldn't have t in there, because I claim that you can replace g naught of k squared t, you can replace this by this, now I put your k squared, David, that you want. So let me now suppose we're doing the Dirichlet problem, so we'll have this function, yes. Now, if I do this, I will tell you a moment that I can't do it, then of course, there is no time dependence in here, Harvey, therefore it's immediately obvious that this representation satisfies the heat equation, just like the interval problem, right? Why is it true? Well, it's obviously it is true, because look, the extra term between this and this is the integral from t to capital T, yes, of E. I have outside, I will get this, is the extra term. Yeah. But this, exactly for the opposite reason of what I talked about before, this is bounded and analytic in here, you see, because this is bigger than this now, as opposed to the previous case, therefore this vanishes, you see. And actually, when you do things rigorously, this formula is better. Of course, from the point of view of physics, this formula is better, because you will tell me what happened to causality if I give you this, yes? If I give you this, you said I have an evolution equation, it cannot be that I depend on future data, yeah? And you see you don't. You have the point. That's the first point. Now, with this replacement, it's another exercise, if you like exercises, another homework. This you can prove in one line, that if you evaluate this equation at x equals 0, and you use the inverse Fourier transform, you recover this function. So now it is absolutely uniform convergent, not a serious problem we had, and that's why I'll show you in a moment. This is very good for computations. Okay. So the second therefore remark is that now it is elementary to show that the PD and the data are satisfied. And now, why this problem can be done by a transform. You see? And this is what I call return to the real line. Return to the real line. You see, from this equation, see, remember what we did. So we started with terms like this, yes, and we went to the complex plane, which means that as long as I have terms like this, Harvey, I can go up and down. Yes? But after I use the global relation, not only I will have terms like this, for which I can come up and down, but I will also have terms like this. And my claim is that after you use the global relation, in general, you cannot come down, because you will not have enough analyticity. But this problem is too simple, because this problem, you have here minus k, and this function is analytic in the entire upper half plane. So you have enough analyticity here to allow you to return to the axis. And if you return to the axis, you will recover the sign transform. Okay? So therefore, return to the real line only in very particular cases when has sufficient analyticity. And then classical transforms exist. Okay? But in general, you cannot return after using the global relation. Okay. Here? And the fourth point, very good if you want to teach this stuff, numerics. Okay. So, all the problems we ever do with students, you see, we give them data for which they can compute these transforms, explicitly. So exponentials or polynomials, you see. If you compute these transforms explicitly, then this integral, will be only an integral in K. See? And what are the properties of this integral? And again, you can do a simple example to see it. What are the properties of this integral? This integral will involve e to the ikx, yeah? And it will involve e to the minus k squared t. Yeah? And as far as the boundary term is concerned, because that's a novel term, yes, we are integrating along here. Okay? Along here, this for large k, for any fixed x, decays exponentially. And what about this? By definition, this oscillates. But of course, when you have an explicit expression, you will see that in general, this has analytic continuation. Therefore, I can replace this contour by this. Yeah? And now this will also have exponential decay. So when I realized this, because I did it by hand, take 5 points in K, it's enough. And this is what we did with Natasha Flyer in this paper, So why emphasize? I emphasize this because I think this is fantastic for the students. We give them a whole course in PDEs, spectral. If you want to do good work, you do spectral theory, etc. And at the end, you tell the student asks the question, how do I compute? And then you tell them, oh, I'm sorry, now you have to go to another professor, take another course, finite elements or finite, and do it. This is terrible, from a pedagogical point of view. This, you spend one lecture, no more than one lecture, and the students will go to their math lab and be very happy because they will find answers, Okay, now let's spend no more than 10 minutes telling you what happens to it now when we go to the finite interval. And things become even more interesting. You see, now there's a surprise. Not really a surprise a posteriori, but for me it was a surprise. You see? So I don't want to write everything, so I'm going to use another color. So I will not give you details because I won't talk a little bit about elliptic, but let me use another color to add the finite interval, yes? So let yellow be the finite interval. So now we have, you see, this is L, right? And of course, you remember, the first step had nothing to do with the domain, the same form, right? But now, remember, I will have to integrate what happened, power cut. What happened to the light? Came back. So when I integrate around here, I will have this contribution. So what will happen is this now will become L. Yeah? Therefore, this now is again a type function like this. This doesn't change. But we will need new creatures, which I will call it HJ, KT, and then here, there will be one more term. Again, this now is going to be for all k, come on, for all k, yeah? And now we'll have another term here, which will be this. The same thing, I don't write here. Correct? You see everything, I hope. There's nothing else, yeah? I just integrate along this term. And then I will have another term here after I use Fourier transform. And this term will be minus 1 over 2 pi, the integral, the same thing. Actually, I have to be careful. It's ik minus ik L minus L. Right? Now, double the number of unknowns. Yeah? But no problem. Why? Because we have two equations now. We have okay, so any questions before we cover this? So all exactly the same derivation, nothing changes, yes? Again, this equation, this is a beautiful representation of the complex plane, but the difficult problem now is that if we're doing the Dirichlet problem, Mr. Harvey, I know this, but now I have two unknowns to deal with. So let's evaluate them. The only information we have is the global relation, yeah? Nothing else. So the global relation now give us this. So let me do it. So what we have? We have e to the k squared t, yes, u kt equals, let me have it g1, right, of k squared t. Actually, I'm not going to write kt because, after all, if I was using this trick, there would be no dependency in t, plus some function which is known. I'm sorry, plus e to the I k l h1 k squared plus some function which is known. And this function involves all the Dirichlet derivative, the initial derivative and the two Dirichlet derivative, right? So this is a global relation. And this is valid everywhere, yeah? Yes? And then I use my invariance, so I will do this. How many equations I have? Two equations for two unknowns. Yeah? So I have this and this to solve. This is known, and I expect that this will play no role. Yeah? So schematically, what I will get g1 k squared equals something known, divided by delta of k, which is the determinant of the system, plus something which will involve these creatures, okay, and similarly h1. The same thing. And this delta for this problem, so you can enjoy it, is e to the ikl minus e to the minus ikl. So let's see what must happen now. What must happen now? You see, I take this and I put it back in these representations, just like we did before, yeah? This part is known, so we don't care about it. But the miracle is that this thing must disappear, okay? In order for these things to disappear, I must have that this creature is bounded and analytic in here and in here, yeah? Well, there are two ways it can lose boundedness. One is to blow up. But look, where are the zeros? Where are the zeros? The zeros are on the real line, you know? And except for k equals 0, which you can prove, it is removable singularity. There are no zeros in here, so no problem with this. So it seems at this moment that I could do something crazy, because it seems, you see, in general, I have two equations with two unknowns. So in general, it seems that if you give me two data, I can do the problem, but it cannot be. It cannot be that you can give me, for example, two boundary conditions here and no boundary condition here. You see? Because the limit of this problem, when L goes to infinity, is not well posed. Something very crazy must happen. So I must be missing something. What am I missing? Am I missing the following? That this, in order for this to disappear, not only I don't want zeros, but I want this creature multiply by either this, because remember this term will cancel, or multiplying by this to be bounded and analytic, and this is the fantastic thing. You can prove that this is the case if and only if you have a well-posed problem. Okay? And that's it. But now you say, all my life I've been doing the heat equation through the sum representation. There are no sums here. You know? What happened to the sum? What happened to the discrete spectrum? That always bombard the heads of the students that if you have a finite interval, you have discrete spectrum. not discrete spectrum. Of course, if you want, you know, this is, remember, this integral along here, this integral is along here, then you say, okay, I have still enough analyticity because you remember, this is huge analyticity, you know. I deform on the real line and I pick up the spectrum and I come back to the usual representation of Fourier. Of course, I recommend strongly against it for several reasons. The first reason is that this is absolutely beautifully uniform convergent and you can do numerics. For yes, it's not. You know? Not only it's not at the one end, but it's not at the other. You have double problem. But it's worse than that. You know? Go to any book that does Robin boundary conditions. If you do Robin, first of all, nobody does Robin and Robin because it's too hard. You know? But when they do one Robin only, you see, then if you remember, the analog of delta now is very complicated, which means that you cannot solve, like here, the zeros of this in closed form. So what they give you for a Robin problem, a series in terms of a transcendental spectrum. What will happen here? What will happen here is if I do Robin and Robin, if I do both Robins, you see, I will get this, you see. So if I have these boundary conditions, this I take it to avoid some point spectrum which I can handle very easily, but never mind. You see, in this case, this delta is this. Let's call it delta of k. Okay? Nothing else changes. Of course, this, again, you can solve very simply, doesn't have zeros in the upper and lower half plane, the zeros. So, what's the difference? This is at the same level as the representation of a Dirichlet or the Neumann problem. You know? So here is the choice. Here is the choice. You see? You can either follow the Fourier methodology and get a series in terms of a transcendentally defined spectrum for a representation which uniformly converges neither at the left or the right, or you can follow the new approach and get a representation which is as explicit as in any other problem, and it's uniformly convergent. But strangely enough, no book has this, of course. And note, if people had used the philosophy of the Watson lemma, in principle, they could start with a usual representation, deform contours, and come. Because, you know, to this, from this, as I explained to you, from this representation, you can come down. So you could have gone up. But nobody did it. But now, let me conclude the evolution equations and go to elliptic for a problem that is a surprise. You see? The problem is, suppose now I do the third order. You see? And I will only, although the algebra is more or less the same, because I'm running out of time, I will only sketch what happens. You see? Let me sketch what happens in the third order problem. You see the divergence form. So let me not take ux, not to have additional algebra problems. So let me take this. By the way, as you see, again, only one boundary condition. You know this, but not many people know that, for example, if I put minus here, I need two boundary conditions on the left. You see? So it's not so trivial. By the way, from this method, it's immediately obvious, as you will see in a moment. So the first step is divergence form, which is this. Okay. Yes, please.
You mentioned that you keep wanting to put things in divergence form, but both of these equations are under divergence form. So I think what you're really saying is I want divergence form with an extra parameters.
You're absolutely right. A family of divergence forms. Absolutely correct. Absolutely correct. A family of what I want is a family of divergence forms. That's absolutely correct. Thank you. Yes. And of course, this reminds me of another important statement due to your good remark that remember, differential geometers have been doing this for a long time. You know, writing equations, but they never introduce a k. This is the whole point. Without a k, I can do nothing. Yes. So now I integrate again. Nothing will change. Yes, I deform the contour, and then the only difference you can show is that rather than having pi over 4, I will have pi over 6, pi over 3. That's all. That's the only difference. Okay. But again, the difficult question is the global relation. Yeah? So the global relation now is this. So this is the transform of the second derivative. This is the transform of the first derivative. Okay. As always, this is imaginary k less or equal to 0. Okay. We know this. We know this, for example. I don't know this. Okay. But now we have k cube, which means there are two roots. So I can let k go to alpha k, and k go to alpha square k, okay, where alpha is e to the 2I pi over 3. Okay. And a picture, as we know, tells everything. Okay. Yes. So you want to be here. Yes. You want to be here. But the global relation is valid everywhere in the lower half plane, right? Therefore, in particular, the global relation is valid here and here. Huh? So I use one transformation and I take this to here. I use other transformation and I take this to here. So in here now, I have two equations for two unknowns, done. Algebra. Okay? By the way, what happens in the other problem when I have minus? You know, when I have minus, you see immediately what happens. You see, I have this picture. You see, but now I am in here, my contours are this and this. My contours are this and this, you see. And the global relation is right in the lower half plane, but remember, these are the only transformations which live invariant, you see. So I can start here. Yeah? I use one transformation, I can go there. I can start here, I can use other transformation to go there, but it means in each of those regions I have one relationship, yes? Which means I have to give to data. Okay, so no surprises for the problem. And then you see what you will have entering. What you will have entering will be u of alpha k and u of alpha square k. And if you draw a diagram, it's clear. Now you don't have enough analysis to come to the axis. You see? One of them can, but not the other. Okay, end of the story, but let's go to the finite interval because this is the first time I got a surprise in this. You see? If you do the finite interval, now the contours for the finite integral look like this. So remember, this was your contour for the half line, and now we got the finite interval, we have to add this. Okay? So we get, we do as before, but now we get some determinant delta, right? And this determinant delta, I have not written it, but there is a beautiful theorem, and this beautiful theorem tells you asymptotically where are the zeros. Because these functions, as you remember, involve only exponentials and k. And there's a beautiful theorem which is asymptotically where are the zeros, and after all, you only care about this problem asymptotically, yes? Because near the origin, for any finite k, you can deform anything you want. And you remember, in order not to have contribution, we have to make sure that there are not zeros here, here, and here. So we can throw the extra terms, yes? And indeed, we were lucky. Of course, it's always the case. Another color. We were lucky. And the zeros are where? The zeros are here, here, and here. Where you don't want them to be. So Beatrice Pelloni was working with me at the time at Imperial. She was my postdoc. So we did this. And because I always associated, finite interval with discrete spectrum, I said to Beatrice, a very nice result. Now go and deform, from here to here and pick up the discrete spectrum. So she called me a couple of days, it cannot be done. I said, come on, of course it can be done. So I look at it and I couldn't do it. You see? And of course, a posteriori, I shouldn't have been surprised, yes? But only recently, people have proven this rigorously. I mean, what we knew is through our method, you could not obtain a discrete spectrum. It doesn't mean that the discrete spectrum, it's not enough. But people now have proven rigorously, and the statement is the following. There does not exist an infinite sum capable of expressing the solution of this stupid problem. How about that?
Even with the minus.
Even with minus sign. So this idea that finite spectrum, finite L, discrete spectrum, infinite, semi-infinite, it's not true. It's remarkable. And with this surprise, I'll stop. Okay? No, but I will continue with elliptic. But do you have any questions about this before we leave the evolution equation? So I gave you, by the way, I wrote down this. There's a guy who has formed a portal entry, whatever, a big web page in this. And if you go to the computer, to the Google and find unified transform or focus transform, it will come. And there are many, many references to this work. 200 reference something of papers written in this business. Okay. Any questions about evolution before I leave it? Okay, let us start with elliptic, and to try to emphasize what is different and what is the same. So the big surprise in here for me was this failure, if you want. So for the heat equation, you have a choice, either continuous spectrum or discrete spectrum. But for the third order problem, you have no choice. It's only continuous spectrum. Of course, there are very interesting questions in terms of spectral theory, which we're trying to answer with David Smith and Beatrice Pelloni. What does it mean from the point of view of spectral theory? Is there any spectral representation of this representation? And they are very nice, these things, but this is not the point to do it. So all I want to do now is tell you a little bit about the elliptic problems. So let me write down everything for the modified Helmholtz, because the modified Helmholtz is as simple as Laplace and a little bit less simpler than Helmholtz equation. So I write down the modified Helmholtz, which is these equations on the left, and the next means I would give you some introduction to this problem. So uxx plus uyy minus k squared u. This is the modified Helmholtz. K is greater than 0. K now is not, from now lambda will be my spectral parameter because k usually people use it for this. Okay? So this is the modified Helmholtz. If I had plus would be Helmholtz. And what I want to do is I want to write down the global relation, which
Do you mean k positive or do you mean k squared positive?
in general I mean k squared positive, but let me fix k to be positive. Yeah, it's up to me. But I don't see the global relation, so I'm sorry about this. I don't have the divergence form, but again you can derive it in a couple of lines by writing this with the adjoint, and then if you choose an exponential, you integrate. So I write the global relation directly, and the global relation is the following. So if this is valid in some domain omega, then the global relation is the integral around the boundary of omega is of E I k over 2 z bar over lambda minus lambda z, and of course I parameterize the boundary by some parameter t, okay, of u Neumann t plus k over 2 u of t of lambda. You understand what I mean? I mean here x of t and y of t, okay, more properly, of lambda dz of t dt plus 1 over lambda So this is a global relation. So this is, if you want, is a general description now of the derivative Neumann map, a true description, you see, because there are no t's, you know. Okay. So for evolution equations, we did two things. One is we wrote an integral representation of the solution in the complex plane. Yes. And I want to do the same, but under very limited case, namely what I want to do the same for a polygon. See? So I take a convex polygon, and there is some, it's characterized by its corners, you see, bounded convex polygon, but you can go to non-bounded. So this is a convex polygon, you see. So the question is, for this convex polygon, can I give you an integral representation in the complex plane of the solution, which is something like the Fourier transform? That's what we did before. So remember, please, what we had before. Before we had some transforms, which were what? Were integrals of the underlying thing along the boundary. And then we had some integral in the complex plane of this. It's exactly the same thing what happens now. So what do you do? On each side, you see, you associate some data. So on the side Sj, I associate, so this is the j side, I associate the data uj of lambda, which is given by the integral from zj to zj plus 1. So along this, yes, of the following, E to the minus I k over 2 okay, it's this, let me write in this form. I don't want to write it. Okay? So with each side, you associate its transform. Of course, once more, unless we know the Dirichlet-Neumann map, we will only know half of this. Okay? But that's what we did also for evolution equations. And then I should give you now a formula for u. Yes? And here it is. U is what you expect. What do you expect? You expect an integral in the complex plane, and indeed it is. For each side, you have an integral. So if I have n sides, I will have this. So this is the integral along some ray Lj e to the minus. The same thing here, but with a minus sign. And here I have just uj of L dl over L. And this beautiful representation, I only have to tell you what this is. So lambda, this contour, Lj, is characterized by this angle, and this angle is minus the argument of zj plus 1 minus zj. There are two ways. There are two ways to derive this, in my opinion, absolutely beautiful formula. You see, as you see, this is nothing but a generalized Fourier transform. You see, and there are similar formulas for Laplace, for Helmholtz, for any little problem you want. You see, not known. I mean, come on, this is beauty. You know, this is astonishing. You know, by the way, you don't see the square roots of the balloon. You see, no, this I understand. This is uniformization, you know, in the complex plane. How can this not be known? You know, I first did this for Laplace, and I went to first person. I went to Henry Manchin. I was for sure he would know it, you know, because it's too simple. Absolutely not. By the way, the derivation from our point of view of integrability is very, very, very interesting, because you look what, you know, just the last 5 minutes, and I will tell you, by the way, it will only take me 5 minutes to explain to you how you can use this equation to get very, very efficient numerical schemes to solve the Dirichlet-Neumann map. Right? I will say that at the beginning of my lecture before I go to waterways. That's all I need to, but let me tell you something about the derivation of this. There are two ways to derive this formula. The first way to derive it is by doing spectral analysis. You see, like I mentioned to you yesterday, that I have a Lax pair, you see, and then I do simultaneous spectral analysis. That was a big idea, you see, or alternatively as a differential form, yeah? Because I have d of nu some exponential, right, equals this. You see? So you want to do spectral analysis for this. What does it mean, spectral analysis? It means, can I find nu which covers the complex plane? And as you remember, in inverse scattering, or for the derivation of or the solution of initial problems, you only have two mu's. One in the upper half plane, which we'll call mu plus, and the other in the lower half plane, which we'll call mu minus. You see? In the analysis of the half-line problem, I had found 3 mu's. And in the analysis of the finite interval, I had found 4 mu's. Now, how many mu's I find? I find n. And this is very, very nice, because look what happens. You see, if I integrate this, I can use whatever you call it, the fundamental theorem of calculus, because it's a closed form, right? So I integrate, and I have this. some initial point. And so if this is called star, right? And this is star. So, and remember, because this dd is 0, it is independent of the contour. So the only thing I care about is the starting point. You see? So what is fantastic? What is fantastic is that if you take for your starting points each corner, right, then you will get n mu's, and these n mu's precisely cover the complex plane. So you get a Riemann-Hilbert problem, you know, for this collection of mu's, and you solve the Riemann-Hilbert problem, and you find the representation. That's how I found it.
So your n is arbitrary.
Arbitrary. Little n is arbitrary. Okay, so now for the last 2 minutes, so this is the derivation of this formula if you're interested. But for me, so finally, this is how I understood why, you see, because in the half-line problem, you see, which is this, how many corners you have? You have 1, 2, 3. That's why I had 3 mu's, you see. For the finite interval, I have 4. You see? So it's a general fact. Spectral analysis for a polygonal domain convex has as many mu's as corners. Couldn't be more natural. Okay, so let me now suppose I do this. I have this polygon, okay, and then if I just have this, nothing else changes. Yes. So on each side, so let me introduce the main idea. The main idea by, so I don't have to steal from water waves. Let me introduce the main idea for a square. You see, I have a square, or whatever, square. Yes? So let's suppose you want to do the Dirichlet-Neumann map, all right? On each side, as you see, I have U and normal. Suppose you give me Dirichlet. That means on each side, I have one unknown, right? So I have U normal 1, U normal 2, U normal 3, U normal 4. I have 4 unknowns, yeah? And by the way, there is a second global relation, which I didn't write. Elliptic problems have 2 global relations. So I say, well, now I have to make an approximation. So let's expand this in terms of some base function. And Fomberg's big contribution was to suggest that we should use Legendre, so you have spectral accuracy. And let's use capital N. This is nu. Let's use capital N constants in the expansion, which means we have 4 times n unknowns. Yes? After this, everything is exact. Why is everything exact? Because when I plug this representation here, all I have to compute is the Fourier transform. But for Legendre polynomials, either you can write the Fourier transform in terms of Bessel, or you can write in closed form, right? So no more approximations. So I have 2 equations, right? So I have, because the global relation comes conjugate, if you want, 2 equations for n unknowns. Okay? I finish in 1 minute. And then you say, well, are you crazy? How are you going to solve you see? But if you look at this, you don't have 2 equations. You have infinitely many equations, because lambda is arbitrary. Right? So it's your business to choose any lambda you want. Second contribution of Ben Fomberg, by the way, was already tenured when I was a student at Caltech. You know, second contribution of Ben Fomberg is to say, don't take 2n points, so you have 4n, but take overdetermined. Okay, and he did this, and so that he can solve the system. And for the square, he got some condition number 10 to the 8. Not very good. You see, we have done this now, but we take special points. And not only we can do it, but we can do it with a conditional number of something like 4 or 5. You know? So that's the idea. The idea is you evaluate this global relation at specially chosen collocation points, and you only have to make 2 choices: how many points you take, and how close they are for each other. And we have some empirical rules for this. And if you use empirical rules, which suggest, then you find condition numbers which are ridiculous. I said 4, 5, never seen anything more than 10. Okay? And that's it. I'm finished.
Thank you. I have to leave, but I believe you
Don't
have
worry.
your questions.
I'll share the session. I'll share my any questions. No, you know everything. You know everything. Anybody else who knows almost everything? No. Yes, please.
What about variable coefficients?
Yeah, that's a good question.
Because
I
you,
don't-
you
I-
mentioned
Yeah.
medical imaging yesterday, right?
Yeah.
And usually it's through inhomogeneous
Yeah,
imaging,
of course,
right?
of course. Yeah.
So-
Yeah, okay. First of all, I'm impressed that you caught this, the medical imaging, but it's a very different business. So here, for this method, so far, this method has only been used for constant coefficients, you see. So what I mentioned with medical imaging is that,
Thanasis? I thought you had a few papers on variable coefficient problems.
yeah, but I had a few, but they are sort of additive. They are not really, there are all,
Not general.
you see, what I mentioned is that for evolution equations, yes, half of your Lax-Baer was this. And of course, you here is anything. Yeah? And what I mentioned is that what we suggested with Gelfand is a new way to do spectral theory for such equations. And this gave rise to a way, so spectral theory means you find a way basically to derive transforms, or another way to invert integrals. So then Roman Novikov was able to invert the attenuated Adon transform, which indeed involves attenuation, therefore it's exactly what you say. But this has nothing to do with his method, you see. So unfortunately, I mean, I think maybe some numerical ideas will come out of variable coefficients, but I don't think analytic things will come. But in terms of elliptic problems, you see, what I forgot to mention is you might say this beautiful formula I wrote down, what is it good for? And the answer is using this and exactly the philosophy of invariance, we can solve some problems that the classics could not solve, you see. But again, very limited polygons, you know, triangles, etc. We can, as soon as you go to more than 3 sides, then you don't have enough invariance to do it. And then I think the main contribution of this method is this numerical scheme. Because I think, you see, for example, Ben Fomberg gave a talk and he mentioned that he used this approach to compute eigenvalues for Helmholtz equation. And he said he had the best code and it would take hours or days, and with this you could do it in seconds, you see. And so I think this is the main contribution of this. How to, at least for polygonal domains, you have a very, very efficient. And again, in terms of students, you know, you teach them, just teach them this problem. Just tell them how you can solve this problem numerically, without anything. I mean, this is so simple. Just take an equation and evaluate at some special point. It's nothing. I mean, it's a joke, but it's very powerful. So my hope is to write sort of a new course, which here I cannot do because, you know, here people are lazy. So at Cambridge, for example, we only have eight weeks of lectures where you can do nothing. But in the States, you could do it because you could give a course on PDEs where you have a 4 or 5 at most lecture numerics to complement it, and then the students will learn anything they need, you know. No need to take anything else. It's true. From point of applied mathematics, you know, you don't need any other PD stuff. Okay, I'll see you tomorrow. Tomorrow I'll start with, maybe I show you transparency of some concrete condition numbers, and then I will do the water waves. Thank you. Thank you.